So we're going to be starting by learning about all kinds of moving objects, but the first chapter that we're launching into is all about one-dimensional motion. Okay? So today we're going to learn how to assign a frame of reference to our problem. Then we're going to learn how to calculate displacement and distance. You probably already know how to calculate distance, but differentiating it from displacement will be important. And then we're also going to be able to calculate velocity and graph velocity.
I heard graphing.
It's not that bad. It's not bad graphing. Okay, so my disclaimer here, this chapter deals only with one-dimensional motion. So objects will be moving back and forth in one direction, but we're not going to move in like two different directions. So imagine, if you will, a number line. We can move back and forth, but not up and down or side to side or anything like that. We will eventually get to motion in more than one direction, not this chapter. So to begin, motion must be described in relation to a frame of reference. Okay? A frame of reference is a system for specifying the location of objects in both space and time. Okay? There are usually multiple frames of reference for any system or problem that you're working on. Some of them are useful, some of them may be less useful for your problem. All right. In physics, we have to keep our frame of reference constant for the duration of a problem. So once we've specified what our frame of reference is, then we cannot change it for the rest of the problem. Otherwise, we will affect our answer. So, for example, okay, if we're looking at a train and this train is moving, okay, some of the different frames of reference we might look at are the stations that it's passing by. Okay? So we could compare its motion to the stations. We could compare its motion to its location on the surface of the Earth. We could compare its motion in the solar system. Or just the known universe, you know. But only some of these frames of reference are useful. And once we pick one of them, then we have to stick with it. So if we're going to talk about the motion of the train, and we think it's most useful to use the stations along its route to measure its motion, then we need to stick to that, as opposed to motion along the surface of the Earth, or cities, or things like that. We want to make sure that we're sticking with our frame of reference, because, again, if we change it, we could affect the problem. Displacement is something we're going to be measuring, and it's the length of a straight line that's drawn from an object's initial position to its final position. We use the formula change in position equals final position minus initial position to solve for this. Okay. So when I explain this to my freshmen, actually, I say, you know, if you start here and you travel all the way around here, squiggly loop, over here, and you end here, your displacement is the distance from where you started to where you ended, not that whole path that you took. In a more simple example of this, okay, I would, let's say, because we want to keep this one-dimensional, if I walk 2 blocks to the store, and then I walk 1 block of that back to my friend's house, okay, then my total distance traveled was 3 blocks. But my displacement is only 1 block because it's the distance of where I started to where I ended. Again, doesn't always equal distance traveled, aka how far the object has moved. So if we're calculating distance, we're just going to add up the total distance you moved, measured in whatever units we are measuring distance in. But if we're measuring displacement, then we're measuring from where we started to where we ended. Also, a displacement is going to need to include a direction. For one-dimensional motion, we are going to assign one direction to be positive and one direction to be negative. In general, our physics book assigns the directions right, east, up, and north as positive directions. So if you're dealing with a problem that's like someone moving north and south, north would be the positive direction and south would be the negative. And they assign negatives to left, west, down, and south directions. So since this is what the book uses, we'll try to stick to this as our convention when we're working problems, because it's likely that that's what the book did. So velocity. For a complete picture of motion, we need to know both how far we went in our change in position, and also we need to factor in speed.
What's the word that I'm missing?
Must. Speed must be factored. So we use the formula average velocity is equal to change in position divided by change in time, or displacement divided by time interval, if you would like different words. You can write that formula out to look like this, or if you would like it in the version that looks less messy, you would say velocity average is equal to change in distance over change in time, which could also be written as final position minus initial position divided by final time minus initial time. So you could write it out like that. And anytime you see this delta, this triangle,
Change.
that means change. So change in time, change in position.
We started using it in calculus today.
Oh, excellent.
Yeah, we're pretty much
Cross-curricular.
on what is it called?
Schedule?
On schedule. I had a word, now it's gone. On the same wavelength as them. We're also on 2.1 in calculus.
So this is an average velocity, which means that the object probably at times moved faster than that and at times moved slower. You understand how an average works. You're a senior. Instantaneous velocity is much more difficult to find. You need like a speedometer for that, whereas average is much easier to calculate because all you need is change in position and time. Velocity can also be positive or negative. This depends on the sign of the displacement because, as you know, time cannot be negative. We can't rewind time. We're never going to have negative time. But if your displacement is negative, then your velocity will be negative. And all that means is that you were traveling in the negative direction. Speed does not equal velocity because velocity includes a direction and speed does not. So you can choose on your homework to either report the direction by using a word like north, west, east, left, right, or you can choose to include the direction by simply putting a sign on your speed, but you have to report a direction. A speed is accurate without a direction, but a velocity is not. And that's why average speed is going to be distance divided by time, but if we're doing velocity, we're using displacement and not distance, because they're just slightly different.
So, wait, go back.
Mm-hmm.
Speed, distance, divided by time.
Mm-hmm. velocity is displacement divided by time, not distance. Remember the difference between distance and displacement.
But we still time from blank to blank, so you're still minusing the time. What are you minusing? Like, how do you get two different times?
The time you started and the time you ended.
Oh, okay.
Yeah.
It's not the duration.
No, you're basically, when you're doing final time minus initial time, you're calculating the duration. So if they just give you the duration in the problem, they say it took 2 seconds, then you don't need to do final time minus initial time. But if they tell you you started at 5 seconds and then ended at 10 seconds, you'd need to do the time minus whatnot. It's very easy in science in general to think that you should get something, and then once it's been explained to you, you go, that was easy, I should have gotten that. But it doesn't matter. If you didn't, then we gotta go back and we gotta get it.
No baby understands that when they push the ball, it's gonna roll, but then they push it and it rolls, and it's like, oh, I knew that.
Exactly. We can also interpret velocity on a graph. Okay, on a velocity time graph, the slope of the line represents its velocity. So you know how to find the slope of a line, hopefully.
Yeah. We went over it in math today.
So here's a sample position time graph. Okay, so you have position on usually the y-axis and time on the x-axis. And so you can draw yourself a lovely graph on a position time graph like this. Sorry, I'm having to wrap my brain back around physics terms because in freshman science we just went over this and we called them distance times graphs, but position time is more accurate. Okay, so on a position time graph, the lines mean different things. So for example, a straight diagonal line that doesn't curve at all is a steady speed, a constant speed. A horizontal line means that an object is stationary, which makes sense, right? Because the distance is not increasing at all. And then if you get this curved line, that means that the object is speeding up. I would also add to this, if the line curves in the opposite direction, so for example like this, that would be an object that is slowing down. And for one-dimensional motion, on a graph like this, we can indicate an object changing direction, because if the slope of that line goes back towards the origin, we know their distance is decreasing, which means that object turned around and is heading back towards where it came from.
What would that look like? It going... Oh, the red one?
Returning to start right here.
Okay.
Yep, so the flat line up here is stationary. This downward slope is returning to start.
And then that's slowing down, that purple.
Yes, that one, the one that I drew on there is slowing down.
Sorry, I just did it on purpose.
Your actual velocity, as we discussed, is going to vary across your trip. So generally speaking, these lines represent an average velocity. So if you want to find your instantaneous velocity, you can. You're just going to have to do some math for it. You will select any point on your graph, and then you will draw a line tangent to that point on the position time graph, and then find the slope of the tangent line, and that will give you your instantaneous velocity. So going back to our image here, whoop, 1 too far. We'd go ahead and we would pick, like, say this, I forgot to turn drawing mode on. We'd pick this point here, if I can make it draw. Then we'd want to draw a line that was tangent to that. So gotta make this point bigger so it's easier. So a tangent line would be like this.
So it doesn't have to start at origin, the tangent line?
Probably should.
Okay.
But the goal is to then get the slope of that line. Your book also has a couple of examples of this if you want to look at it.
Okay.
In your text as well.
I think it would be hard if it started at the origin for some ones,
For some
because
lines,
you would
yeah.
touch it twice.
I don't think it has to start at the origin. I think you can just draw a tangent and then find its slope. Okay, here, we'll go back to these. And that is the end of the notes for this section.
Oh, perfect. Perfect.